so this is really the compounds chapter. Let me flip over there, see if I have an oxidation state problem that's super exciting. If not, I'll make one up that's exciting. Yeah, I'll make one up probably. Let's do kind of a medium difficulty one and then a harder one. Oh yeah, I like that one. You can start working on it. I want to know for that compound what the oxidation state is. Really, all of them for fun. And then let me write another one if you're working ahead on that one. Okay, I see where I'm going here. Okay. All right. Yeah. Okay. All right. I think that works for the second one. Okay. And for the second one, I want the copper. Okay. All right. For both of these, you kind of do them the same way. You want to look for things you recognize. So, for example, in the first one, hopefully you recognize that this is what ion? Dichromate. In fact, if you wanted to name this, what would you name it? Aluminum dichromate would be the correct name. Okay, so dichromate is one of your polyatomic anions. So what you would do is you go Cr2O7 2 minus. So now this is a whole, now you have to analyze it. There's 2 chromiums plus 7 oxygens. Oxygen has what charge usually? -2, nice. And the overall, oxidation state, the overall charge of the species is -2. This -2 is from this -2 right here. Okay, so that is from that. You now just solve it like it's an algebra equation. 2 chromiums minus 14 equals plus, -2. 2 chromiums, I'm going to add 14 over there, that's plus 12. So chromium equals plus 6. Not one of the oxidation states you memorized for chromium. You learned which 2 for chromium? 2 and 3. 6 is probably the third most common that you'll see. Oh, by the way, I almost desecrated this place. Let's do that. We'll feel better. Okay. Next. So here, same sort of thing. You want to see what do you recognize. So K has what common oxidation state? Plus 1 OH. Minus 1 H2O. 0. Okay, so you go plus 1 plus Cu. Plus 3 minus 1s for OH, plus 3 zeros for H2O equals the overall charge of the entire species. Notice that there's no number superscripted there, so that's why we put a 0 there. So copper, we've got a -3 and a +1. Looks like we got a -2. Plus 0 equals 0, so copper equals +2. What were the common oxidation states that you remembered for copper? 1 and 2, so that kind of makes sense. Copper, this is the cupric ion. Okay, so there's some oxidation state examples for us. Check. We did a little bit of nomenclature. Any quick questions on that before I move on to nomenclature? Okay, let's do some nomenclature action now. Okay, for nomenclature, remember there's really 4 areas, but 3 are the main ones. So we've got ionic, that's when we have a metal in there. We've got molecular, when there is no metal. We've got aqueous acid, when there's an H in front. And then we've got the organic straight chain to what's called alkanes. So let's go through a couple examples and see how we do. Okay. Nope. like it. All right, so what category is this? So you see a metal, so it's ionic. You want to ask yourself, do I see a transition metal? Yes. So you may have the opportunity to name it in English or Latin. If you're in some of the other classes, depending on your instructor, either they teach you the Latin equivalent now in 2A, or they wait for you to be totally surprised in Chem 2C. Depends on your instructor. Okay? So you might not know the Latin, you might not have to worry about that in other classes. You'll get surprised about that later. Okay, so what's the oxidation state of, what's the name of this thing right there? Thiosulfate. It's a -2. This one is +3. 3 times 2 is +6. -2 times 3 is -6. So it gives the neutral overall charge for the compound. So we've got, let's do English, that would be cobalt. First name as is. 3, Roman numerals, space, thiosulfate. Okay, done. If you wanted to name it in Latin, there's no Latin equivalent of cobalt, but you want to think, what are the two common charges of cobalt? They are 3 and 2. So if you wanted the Latin equivalent, for my class at least, you go cobaltic, ic, for the first name. So that could work if you like that action. All right, let's try another one, just to make sure we got this down. Yes, let's do this for fun. Okay, this is also an ionic. It also has a transition metal, same transition metal. What's the oxidation state of sulfur? -2, same as up there. So this has to be +3 again. So same first name. Cobalt, I'll just write the English, cobalt 3, but the last name is sulfide. Okay, so cobalt 3 sulfide, cobaltic would also work. Let's try another one. I need another blank. Oh yes, I like where I'm going right now. Okay, so this is what category? Aqueous acid, usually on the test, just to clarify, I'll put AQ on the back. Yeah, this is aqueous acid. What's the name of that thing right there? Oh, okay, let me just ask another question. If I had you name that by itself, you would write what? Carbonate, ion. Yeah, if it's all by itself, you got to put the ion at the end. What if I had you name this? Yeah, hydrogen, space, carbonate. That's R, carbonate. Still wrong. Yeah, that's an R, sorry. Carbonate, ion, not acid. It's not neutral. Acids are neutral. That's an R in that big, ugly smudge that's totally unreadable. Okay, so this, it's a carbonate ion. This is neutral. This is an acid. I'll do the easy part. Last name acid. First name is carbonic. Ic, because it's from ate. A to E changes to ic. Okay, next. Okay, all right, this is a binary, meaning it's 2 different types of atoms only, where this was a ternary, 3 different types of atoms. So the prefix, the first part of the name when it's binary is hydro. Hydro tells you that there's only 2 different types of atoms. Then the iode, and what's the suffix? Ic, hydroiodic, last name, acid. Okay. Let's try that one. Okay, what is this category? This is molecular. There's no H in front, there's no metal. It's just non-metals. So now what is special about this naming? You name what? The subscripts, the numbers in the subscripts. You don't do that for anything else except this one. Everybody likes to get these wrong on the test and name the subscripts for all the rest of these. No. Just for the molecular is when you name the subscript. So this is dinitrogen, tetra. Now this really, because there's 2 vowels, it's you don't put the A of tetra, it's tetroxide. So prefix tetra, ox is the stem name, IDE for the end of any molecular. Let's try one more. Again, sometimes some of the other instructors don't cover organics, so I don't know if this would apply to the other classes. It applies to mine. Let's say I had you name that. How many carbons do you see? One, two, three, 4, 5, 6, 7, 8. If you're in other classes, have you seen this kind of stuff yet? All right, have fun for the final. We're going to see it for sure. It'll be fun times. Okay, so 8 is octane. I prefer to do the beginning quarter. Some other instructors might do it at the end. So other classes might not have to wait for this exam. You can freak out during the final. Okay, oct, and the suffix is ane. All right, any questions on any of these before I go on? I'm just trying to move kind of fast so that we get through a lot of these categories. Yes?
If you had 4 iodines, what would you do? Like, would it be tetraiodine?
If there were more iodines here?
I mean, for like the molecular compound?
If there was molecular, like there's a molecular that looks like this. What would that be called? Anybody? What's the first name? Nitrogen, last name? Triiodide for that one. Nitrogen, triiodide for that one. Okay, I'm looking to see if I have an example of a combustion analysis, because that would be both, that would fit into our next category quite well. I want to finish up this chapter and then we'll move on to the next one. Just blitz through this craziness. Okay, let's see what I got. Kind of go from there. There's something here I remember. Oh yeah. I have something. Yeah, this will work. This will be kind of, in the combustion analysis category of empirical molecular formulas. Sorry, I didn't send this to you because I didn't know what you would ask for, but we'll try this. You can take a picture of it if you don't want to write it down. Okay. Let's give it a shot. Got an organic compound, thiophene, CHS is what it tells us. So I just put XYZ. And when we're finding the empirical or molecular formula, we want to find the subscript. So we want to find what X, Y, and Z are. It tells us there's carbon, hydrogen, and sulfur. We know that there's 1.086 grams of this. Okay, this combusts. So combustion goes to CO2 and water. It tells us that. Carbon dioxide, water. This has an additional product. SO2, sulfur dioxide. Why do you think it has this product? Because there's sulfur in it. So because, let's say you haven't seen a combustion that has sulfur in it, I'd have to tell you what that third product is. That's why I tell you all the products in words. CO2, or carbon dioxide, water, SO2. Usually you just see carbon dioxide, water. This one also has SO2. So we know the amounts of each of these. 2.272 grams. 0.465 grams, and 0.827 grams. Okay? So I want to know the empirical formula and ultimately the molecular formula. What's the key unit I care about in these kind of questions? Moles. If it's an empirical formula question, moles is your key unit. You want everything to go to moles of each atom, carbon, hydrogen, sulfur. One thing we ask when we're doing these empirical formula combustion analysis questions is there oxygen in the compound? Yes or no? No. How do I know that? It says so. Okay? Carbon, hydrogen, sulfur. There's no oxygen. Okay? So you're not going to consider oxygen in the solving process for this compound. Literally because that's what it says. Okay. So if you're reading the question, it will direct you whether there's oxygen in the formula or not. So what you're going to do is you're going to go for each atom, carbon, hydrogen, and sulfur. We're going to start with carbon. Carbon is located only in CO2, so we're going to start with that. That's grams of CO2. We're going to change this to moles. Moles, and there's 44.01 grams per mole of CO2. That's found in the periodic table. And then I want to change this not to moles of CO2, because it's CO2, I want moles of carbon. There's 1 mole of carbon in every 1 mole of CO2, or in other words, there's 1 carbon atom in each CO2 molecule. This turns out to be 0.05162 moles of carbon. Okay, remember, key unit is moles, that's why I'm going to moles. This is also what variable? This is X. Not quite, but it's pretty close to X. Next, hydrogen. Going to the next atom, hydrogen. That's only found in water. 0.465 grams of H2O. The molar mass from the periodic table, to change it to moles of H2O, is 18.02 grams per mole. There's 2 moles of H for every 1 mole of water. Or in other words, there's 2 hydrogens in every 1 water. So this, I calculated ahead of time, I got 0.0516 moles of hydrogen. That is what variable? Y, exactly, the Y variable right there. Okay, last one, we're going for sulfur. Let's go for that one. Sulfur is only found in SO2. That's 0.827 grams of SO2. I don't want SO2. First I want to go to moles and then to sulfur. So from the periodic table, there's 64.06 grams per mole of SO2. And then there's 1 mole of sulfur for every 1 mole of SO2. Meaning there's 1 sulfur atom in every SO2 molecule. This turns out to be 0.0129 moles of S, and as you may have guessed, this is the variable Z. Okay, from the original formula up in the upper left-hand corner there. So I've got X, Y, and Z. Let's move this out of the way. Now I'm almost there. I'm really close to finishing, but not quite. I have 1 more step. Oop. That last step, let's write this out. I've got CX, let's write out what we got. HY, SZ, so just putting these in for the variables. According to the law of multiple proportions, these have to be whole numbers. So atoms combine in small whole number ratios. So I need to divide all those 3 numbers by the smallest. That is sometimes difficult to discern for some people, so make sure you can determine which number is the smallest. It's this one with the sulfur. If you do that and round to the nearest whole number, you'll get this. This is the empirical formula. Okay? Now for the next part, I want to do the molecular formula. For the molecular formula, it gave me in the question 84.1 U. Remember U, if you forgot, is the same as, not the same, but essentially similar to grams per mole. It's just the microscopic versus the macroscopic unit. I need to divide the given number by what number? Molar mass of? Yeah, the empirical formula, which is this one. So I need to use a periodic table to find the basically the empirical formula. I did that and I got 84.142 grams per mole, or microscopic is U. For those math savants over there, this looks like it'll be approximately 1. So that means this is C4H4S. Same empirical and molecular formula. You don't know how to draw out the empirical and molecular formula yet, but at the end of the quarter, you'll be able to draw something like this. It'll be that. But you don't need what's in brown here written to the right. Just for those who want to nerd out. Okay. Any questions on this before I go on? Yes? This one right here? Great question. Where did I get this number in the denominator? It's from the periodic table, calculating the empirical formula. So it's always the molecular formula divided by the empirical. You get a number. In this case, I got 1, so I'm multiplying 1 through all these subscripts. Remember, the key unit for empirical formula is molar mass. So that's why I'm using molar mass down here. I use moles up here. Okay, any other questions? Yes? What if there was oxygen? If there's oxygen, there's a whole series of events that happen that are super exciting. I'll show you my reader just to review, but I don't have an example for you now. If you have a specific example, I'm happy to solve that later when we get to specific questions. But let me, I'm going to page 19 of my reader. If there is oxygen, after you find the moles of carbon and hydrogen, and if you know there's oxygen, or if you're unsure if there's oxygen, what you're going to do is convert both moles, in this case X and Y, and really sulfur, if there's sulfur too, all over to mass. And then you're going to say the total mass of the original compound. Notice we never used the number 1.086. It's irrelevant unless there's oxygen. If there's oxygen, that number is this mass total right there. So in that case, you got the mass of hydrogen and carbon and maybe sulfur. And then you got the total mass. You subtract that out, you have the mass of oxygen, convert that to moles. And then that's another subscript. Okay, so make sure you can do that as well. That is a possibility to see on an exam if it's combustion analysis with oxygen. Okay.